All right. So, no course on GPU programming kind of is complete without showing a plot of something related to performance, right? So let me start with a plot here. Uh, so this is about very old days. Probably many of you were not even born. Pradeep and I were also not born. 1976. So these are called as good old days for software. What that means is that you are writing your program, right? Let's say C program or Fortran program, and then at the hardware that you have access to, you run it, and let's say it takes 10 seconds for that program to run. Over years, newer and newer hardware come up. What you do after, let's say, 5 years is that you take your same program, which was written 5 years ago, and run it on a new hardware. And the same program, instead of taking 10 seconds, now it probably takes 2 seconds. And that's amazing because you can go and tell your manager that, see, my program was 10 seconds expensive, now it is taking only 2 seconds, right? So that's progress in some sense. Although you have done nothing to achieve that progress, what was done is essentially done by your company where they bought new hardware. Uh, and this way, the programmers were able to achieve better performance for their codes without modifying the program. Right? And this continued for several years, early 2000 time frame, or maybe late 90s, I should say. Right? So this automatic performance improvement is the one that we were able to achieve earlier. Uh, and this continued. And what essentially allowed us to achieve this is because the hardware was getting better and better. So in terms of, for example, clock frequency, which defines the speed of your CPU, we could see that over years the clock speed went on increasing, and it was expected that at some point in time it will go on increasing and we will be towards a brighter tomorrow. So that we can see towards the early part of 2000. So this was the expectation. Unfortunately, that didn't happen. The reason being that the amount of power that we required when we are clocking our CPUs at such a high frequency, that turned out to be prohibitive. And to illustrate how much power we require, this is another plot which is from Avi Mendelssohn's slides. So these x-axis defines the technology or the size of the smallest area. In some sense, that is defining the amount of area that we use. That is the technology that we use, 7 nanometer technology, right? So that is the right-hand side, rightmost one. So as you can see, the technology is improving and you are able to compress more and more transistors into your same amount of area. And what y-axis shows is the amount of power dissipated. And if you go on following this trend, so starting from, let's say, i386 to i486, Pentium, and so on, when you were at the Pentium scale, the amount of power dissipated was similar to what a hot plate is going to have. And that you can still see. I mean, when you charge your laptop, for example, or run some large cost expensive program or memory hungry program or CPU hungry program, it's going to heat up quite a bit, right? You cannot sometimes even hold your laptop on your lap because of this heat. But we continued and we went to other versions of Pentium all the way. And if you followed that trajectory, it was possible that the amount of heat that gets generated is going to be something similar to what a nuclear reactor demands. If you go further, it is going to be something similar to what a rocket nozzle is going to generate. And later it's going to reach a sun's surface, right? So this was something which was projected. We thankfully didn't reach there. But this showed us the trend. And this was a little prohibitive, not a good sign at all, because we didn't want to get heated up with our machines. So that brighter tomorrow that we were anticipating actually did not reach. And what happened was that there was a tapering of the clock speed, which disallowed us from getting further and further performance. So if you go back to our discussion about good old days of software, what got achieved because of this clock frequency being reaching some sort of a saturation is that we could not take our old program, run it on a new hardware and expect it to give better performance. Right? If there was a way, then the only way was to go parallel. Right? But what do we require to get parallel? Right? So if you look at this ILP, that is instruction level parallelism that you can achieve, that was tapering. That is the amount of parallelism that you can extract out of a sequential program. That was tapering. Then if you look at the amount of power, that was tapering, right, as you go towards further years. If you look at the clock speed, that we saw that it was also tapering. The only thing that was possible was that the technology was improving such that we were able to push more and more transistors into the same chip area. So that was increasing, but then because of the power, we were not able to use all the transistors. So it would be like you have large number of transistors, but at any point in time, you are going to use only part of the area because the power requirement doesn't allow you to go and use all the transistors that are available. So the idea was that, okay, then we are going to make use of this not for a single core, but probably multiple cores, right? We cannot push this only for running a sequential code. We have to go parallel. And that kind of, I mean, parallel programming has been there since very old days. I mean, since the days we saw, even late 70s also there were parallel programs. It's just that it picked up quite a bit in the early 2000s. Right? And if you look at the number of flops, flops is a measure of performance. So flops is floating point operations per second. So there are different number of floating point operations. When we were in the early days, we had kiloflop as the measure, then megaflop, gigaflop, teraflop, petaflop, etc. And now we are in the exaflop era. And the companies wanted to achieve these milestones. What that means is that can you run these many instructions, for example, 1 into 10 to the power 15 instructions per second or floating point operations per second using a farm of machines. It won't be possible using a single machine. It has to be done by a parallel computation. And that we are now in the exascale era, although this plot is a little old, but this conveys how we have gone up in the trajectory of achieving better and better performance. And when it comes to these parallel platforms, I'm going to tell you what are the different parallel platforms. GPUs is just one of them, but there are multiple parallel platforms that we are aware of. For example, we know about the multi-core processors. All your laptops, all your machines are currently multi-core. These are called as shared memory systems. That means that they have multiple cores and all of them share the common DRAM, which is accessible from all the cores, that is all the threads which are running on these cores. So one thread can write the data into one memory location of the shared memory, and the other thread can actually read from it. So then that way they can communicate from one thread to another. We have distributed systems, which is also a form of machines. So all these different multi-core machines, you can club them together either with a wired connection or wireless connection, and that forms a cluster. This distributed system is the kind of underlying system which you use for your cloud computing applications. What we see is just we are using Google Docs. At the back end, there is a distributed system which is going to take your code and run it on different machines. Similarly, there are GPUs, which are also called as many-core processors, which are going to be discussed further in this course. But then there are other accelerators also. For example, there are field programmable gate arrays. Right? So after you manufacture them, you will be able to configure them such that it suits your needs. Maybe later you figured out that maybe this particular portion was better handled, or this particular application could be better handled using these better rewiring or better gate connections. So that can be done in the field meaning at the customer end. So that can be, that is a very advancing area currently. And then there are application specific ICs, which means that I don't design a general purpose computer, but I generate a circuit which is going to be used, or I synthesize the circuit which is going to be used specifically for a certain application. So it's a domain specific IC. And a combination of all of these could involve a heterogeneous system, which might involve certain GPUs, certain machines. Different machines might have different kinds of ASICs, FPGAs, GPUs installed on them, and all of these might be connected in a distributed setup. So that forms a nice heterogeneous system. Any questions so far? All right. So I'll move ahead, but feel free to ask questions anytime. This is a plot which shows a slight comparison between the GPUs and the CPUs. And this, so if you look at the green lines, those are from the NVIDIA GPUs, so single and double precision, that is 32-bit versus 64-bit. And then there are Intel GPUs, which also show the performance of the Intel GPUs in the blue lines. And as you can see, there is a large gap between the two, but this comparison is not apples to apples, because the number of cores that we talk about are going to be very different. The cost is going to be very different across these. So you should not view CPU and GPU as rivals of each other. I mean, as programmers, we should look at them that we are going to make use of CPUs and GPUs together, which will suit different parts of your application. So both are going to be useful in our application, and that is how we should look at the CPUs and GPUs, although the companies might keep fighting with each other, right? My CPU is better, my GPU is better. But we as programmers will make use of both, because for us the application is more important. Om Kumar is asking, can you explain cluster once more? Yes, so cluster is going to be a distributed system where there are large number of different machines. Let's say all of you are seated at different locations, and you have your own laptops. You might be able to connect those laptops together in a wireless manner if you are seated geographically at different locations, and that forms a cluster. Now, if I want to run an application, I can give some data to each of the laptops, and all of your laptops together can work out that application and give me the result. Right? So that is one way in which you create a cluster. A typical cluster that gets created in a server farm is typically connected via a wired network, where there are machines housed inside a building or in a big room, and those are connected using a fast interconnect. Right? Typically, it is going to be much faster, let's say 10 Gbps. And that interconnect allows communication across these nodes to be very fast. And together it creates a cluster, right? Where individual machines can still have their own GPUs, their own multi-core, multiple cores associated with them. So each computer will be a shared memory system, whereas together this is going to be a distributed system, because there is no common memory across them. You are going to have memory in each node in each computer, but not something which is shared across computers, right? So that becomes distributed. Any other concerns? All right. So in this particular course, we are going to discuss further. Yeah, so there is a question from Koti. Does cloud instance come under cluster? The clouds are installed on a cluster. So the underlying hardware, the underlying infrastructure uses a cluster. Within that, the cloud environment requires you to have other software components also. For example, you might want to virtualize some part where you want to run certain applications on certain nodes. You have to take care of load balancing, etc. All of that is handled by the cloud service provider or the cloud instance, whereas the underlying infrastructure is the cluster. Not that you cannot run a cloud from a single multi-core machine, but it's going to be really very slow. It's not really the proper usage of a multi-core machine. All right, so in this course, we are going to have dividing it into 6 different topics, right? So the computation part, the memory part, synchronization, then we'll discuss about certain topics in CUDA. Then we are going to switch gears and talk about the C++ programming specifically targeted towards NVIDIA GPUs. and then C++ programming for generic accelerators like Intel GPUs, etc., which we'll be able to study as part of this course. I should mention that there is a assignment for each topic. So that means there are 6 assignments, and from the perspective of certification, we have said that if you solve 5 of them, at least 5 of them, we encourage you to solve all 6 of them. If you want to learn the best out of this, you should do all 6 of them. But if you submit 5 of them and those are reasonably correct, we are going to allow you to have a certification for this course. To allow you to have understanding of the assignment, we have a separate session planned on Thursdays from 5 to 6 at the same link, at the same WebEx link, where you can discuss your issues with the TA. So let's say that, so the assignment is already posted, and we'll post these assignments every Monday. So assignment will be visible to you. You'll be able to go through this and discuss with the TAs on Thursdays. It's not compulsory to attend, but it's recommended because your doubts will get cleared and you'll be able to sort out issues very easily. And there is also a possibility that the top performance in the course may receive an opportunity for an internship at KLA next year in the summer. So that's kind of an added incentive for you to submit your assignments with rigor as well as sincerity. Pradeep, you want to add anything here?
The only thing I would insist is, the assignments are definitely the key portion of learning for this course. So please, take the time to do the assignments. Leverage the help from the TAs. Sandeep, I'll answer your question of what is KLA in a minute. But leverage help from the TAs. They have given time to you to answer the questions. We will post the assignments every Monday. The assignments will be due end of day Sunday the following week. So since the assignment for this particular topic, the assignment is already posted, so it will be due on Sunday, 26th midnight India time. So please make sure that you turn the assignment in. And to further incentivize is why we've opened this opportunity for doing an internship at my company called KLA. Sandeep or others, if you're curious to see what's exciting, you just go to kla.com. You'll understand what we're doing. And I am the director of a research lab based out of IIT Madras Research Park, where we do research in the space of compute parallelism and AI algorithms. I think that's pretty much a spiel from my side. Okay. Thanks.
Sure. Thanks, Pradeep. All right. So with that, we are going to get into the computation part. Just a little bit of aside, which I tell my students, especially in the online setting. So I'm going to tell you also. So keep your hands away from mouse, keyboard, and WhatsApp if you want to get the best out of this course. Solve questions. We'll ask you questions during the our discussion. So solve those questions yourself. Think about various approaches and take down notes if required. Right. So go back to your school mode and do that. More importantly, ask questions. If you have not understood anything, please feel free to ask anytime. Of course, at times I might get in, or we might get into this mode that, oh, I want to cover this much syllabus. But we will take these questions at the end sometimes. But please feel free to ask questions anytime. Yeah, so that is something which I wanted to discuss. Sandeep has a question: how assignment should be submitted? There is a form given in the Google Sheet. There is a link given for assignment submission. You just go there, choose the assignment, and submit your file. Okay. All right, so let me unshare this and start sharing my computation slides. Just give me a minute. So stopping to share, and now I'm sharing the computation. All right, so let me delve into this. So let's come directly into the coding part, right? So this kind of code, I'm sure everybody has looked at. Right? What does this code do? It just prints hello world, right? So this is our simple C program, which we are aware of. And I can compile it with NVCC. NVCC is a compiler from NVIDIA, which you can compile your file name. The file name needs to be some .cu file for CUDA. And I run a.out. Right? What is the output I get? Well, it should print hello world, as Sandeep is saying. Yes, it should print hello world. But that is not very exciting. Let's go to the GPU part. Right? So in the GPU part, but what the takeaway from the previous slide was that you take any C program and compile it with the NVIDIA compiler, the GPU compiler, your code will compile and run sequentially on the CPU. It will not run on GPU. So all your CPU codes you will be able to run using, compile and run using NVCC. So let's come to the GPU hello world part. So what we want to do is to take this code and run hello world on the GPU. So it's going to require us a few changes to our code. First of all, we have to include this CUDA.h. Right? The second thing that requires is that instead of creating only a function, I'm going to mark that function as underscore underscore global underscore underscore. That defines that this is some function which I should run on the GPU. In that, I'm just going to use a printf hello world. From main, I'm going to call this function, and the way I call it is the function name, and these are the parameters. But in between, I need to specify something. That's something I'll explain, but essentially it means that multiplication of these two numbers defines how many threads are going to run this particular function. Right? So it is 1 into 1 in this case, which means that it is going to run with one thread, and we'll discuss how to make it parallel. So if that is the case, what do I expect is that when I run this program, then I should do a GPU-based computation, and the GPU should print hello world. That is the expectation out of this. So this is our first hello world program. When I, so this is called kernel, and this one is called as kernel launch. So when I compile it, it compiles fine. But when I run it, I don't get any error. I don't get any hello world printed because of this. And that happens because it so happens that when the kernel gets invoked, unlike our usual functions that we call from C, this is not blocking. And what does that mean? That means that the CPU is going to call this kernel or launch this kernel and just moves ahead with respect to its execution. So there is an asynchronous call to the GPU kernel, and that sometimes the printer that gets written or some output that gets written by the kernel, that might not be visible by the time the CPU finishes its execution, and therefore there may not be any output. It will be nice if there is a possibility of making this code synchronous, that is, the CPU waits for the GPU to finish its execution. Right? So that gets done using something called as a CUDA device synchronize. CUDA device synchronize allows this kernel to finish on the GPU. It waits before executing any piece of code on the CPU after this, right? And therefore it makes sure that the buffer which contains this hello world gets printed to CPU's screen or CPU's output buffer, and therefore we see the output to be hello world when we insert that CUDA device synchronize. Okay? The takeaway from this is that the CPU processing from main and the GPU kernel, these run asynchronously. Right? So that is one takeaway for us. Any questions on this, please feel free to ask. Yuraj is asking NVCC -- version. Yeah, you can install the latest CUDA version here. So feel free to use 11 point something as the CUDA version. Most of the programs that we are going to see will also work with the earlier versions, but it's best to use the latest version in your setup, right? Where can you run these codes? You can run these codes either on your laptop if you have a GPU install, NVIDIA GPU install, or you can run these on Google Colab. The instructions to use Google Colab, there is a video, just 5-minute video corresponding to that, which is also linked from the Google Sheet that we have shared, and how to use Google Colab. So feel free to make use of that at the end of our lecture. Jagdish is asking, can you explain CUDA device synchronize? CUDA device synchronize allows the CPU to wait for any GPU related processing to finish. In this case, the GPU related processing is calling this particular function or kernel, which we call. So until that kernel is over, the CPU is not going to proceed. So if there is a printf at this point, that printf is guaranteed to be executed after this hello world, if there is a CUDA device synchronize. If there is no CUDA device synchronize, then it's possible that this hello world may get printed, may not get printed, and in addition, if there is a hello world here, if there is a printf in main after dkernel, that might get printed before this hello world, because these two are running in parallel. The CPU and GPU are running in parallel. Okay, so I was kind of assuming that we are already aware of this, but let me mention this. This might be coming from what is the meaning of why this is happening. So CPU is a separate piece of hardware, and typically GPUs are another separate piece of hardware. GPUs have its own cores, GPU has its own memory, and therefore, and these two are connected via some sort of a bus, which is called as a PCI Express bus. These two are going to be independent entities. That means that whatever you do on the CPU, that is not affecting what happens on the GPU, and vice versa. You will have to coordinate the data transfer across the two via this common bus. There is also some notion of an integrated GPU, in which case the CPU and GPU are going to be on the same chip, and they might have access to the common memory, but by and large what we will be talking about are discrete GPUs, where CPUs and GPUs are separate. Okay, Vandana is asking what's the difference between multiple threads running on CPU and on GPU. On CPU, since it has a separate hardware unit, it has its own cores, and therefore it might run your program on those cores on the CPU. When we want to run this program on the GPU, we'll have to offload the computation. We'll have to run it on the accelerator, which we call as GPU, which is associated with the CPU. So both these CPUs and GPUs can run simultaneously. That means that you can perform some computation on the GPU and another computation on the CPU at the same time. So that is the kind of heterogeneous computation, or CPU-GPU simultaneous computation which we will be doing. Om is asking, can you explain what is the meaning of dkernel? Dkernel is a function which should be running on the GPU. Dkernel is a function which should be running on the GPU, right? And which we need to call from the CPU. So GPU does not directly start executing. It always starts with our main in C, and then from there we offload certain computation to the GPU. In this case, I am just running printf, but in general, we will have a large amount of some parallel or data parallel computation which we would like to offload to the GPU. Meanwhile, CPU could either wait for this computation to be over, or it can perform some other processing, because these two are kind of independent. The CPU and GPU are independent. Okay? All right, so we'll move ahead. So, can somebody tell me what will be the output of this code, and what is going to be the execution of this particular code in terms of what codes can run in parallel, etc. I'll wait for a few seconds for any answer.
It print 3 times.
Okay, so okay, Sandeep also says the same. Om also says the same. Vandana says print 1 time. Okay, good. All right, so Eklavya also says print 1 time. Okay, so let's understand what is happening. Okay, Nitin also says 1 time. Okay, good. So let's understand what's happening. So at this stage, we call a kernel on the GPU, right, with 1 thread, and therefore this, if it gets executed, it is going to print this hello world 1 times. After that, we again call dkernel the same function, right? So this is like calling the function 3 times from the CPU, just that instead of calling it on the CPU, I am calling it on the GPU. And then what does the CPU do? It waits for all the processing on the GPU which was done prior to this CUDA device synchronize, and after that the CPU is going to print on CPU. It so happens that these three can get executed, and therefore you will see three hello worlds getting printed, and only after that on CPU is going to get printed. Okay. But what about the three hello worlds? So let's say that the first kernel would have printed hello world 1, hello world 2, and hello world 3. Suppose for our discussion we assume it to be that way. Then can there be an interleaving between these hello worlds 1, 2, 3? Can it be like 3, 2, 1 or 2, 1, 3 like that? That doesn't happen, and the reason being that all the functions or kernels that get launched on the GPU, they by default go into a queue, command queue. And this command queue is emptied sequentially, which means that the first kernel is going to get queued up by the CPU. It will get executed sometime, right? That we don't know because CPU and GPU are asynchronous. Then the CPU goes ahead and pushes the second instance of D kernel to the same queue, same command queue, which will get executed sometime, and then the third one. This command queue is emptied by the GPU driver one by one sequentially, and until the first one is over, the second one is not taken for execution. And therefore kernels by default are executed one after the other if you push those into the same command queue, which is what happens by default. If you have, there is a way in which the kernels can be pushed to different command queues and they can be executed in parallel, but for now let's assume that these are going to go into the same command queue. I mean, not assume, that is what happens. So CPU launches these and goes ahead and then waits at this point. So it is never going to be the case that on CPU is going to be followed by some hello. That is never going to happen. On CPU will always be the fourth printer. And in addition, hello world 1, hello world 2, and hello world 3 are definitely going to be processed one after the other sequentially. Okay. All right, so that is a small classwork which I thought I'll share, but let's do one more. I'll probably leave this as a homework exercise in the interest of time, but please think about what all is going to happen when I insert some CPU related functions in between these, right? Okay, so that you can try it out at home, and if you have any questions, feel free to post on the group and we can have a discussion, right? Your friends might be able to help us in understanding what all can happen. At the same time, please run these codes on your laptop, on some GPU, either on Google Colab or on laptop, and try it out. I think that will be the best way to learn this. Okay, but all of this was fine. This was all sequential. Let's make it parallel, right? So when we were launching this with a single thread, it will be a good time now to make it parallel, right? So another homework is that find out where NVCC is, that is the NVIDIA compiler, C compiler. Find out the CUDA version. So we had that discussion which Yuvraj was saying. So he has already given the answer, but essentially you can check what the CUDA version is. And you can also find out what is the device query and where it is, right? So that is going to be your homework exercise. Okay, so let's make it parallel. There is a question from Sandeep. Does it generate 3 different threads or uses the one thread 3 times? So it's going to launch the kernel on the GPU. Does it use the same thread to run the second kernel? Well, it's like a scoping in functions, right? So when we say that the function, once it is over, it can define the same variable again at possibly the same memory location, but it's a different memory. It's a different variable. In a similar manner, this thread will be able to say that all the threads are going to get terminated once the kernel is over. So a new thread is going to get created, although its thread ID might turn out to be the same. For example, thread 0 in this case, for the first kernel, second kernel, as well as third kernel, but these are not going to maintain any information, local information, which was created across thread invocations, right, across the kernel invocations. Does that mean that you cannot share data across different kernels? You can, and we'll see that shortly. That first kernel writes something and the second kernel reads from that modified data. That is possible. All right, so what we are going to do now is that I said that these are going to be, multiplication of these is going to be the number of threads which are going to launch the kernel, right? The number of threads which are going to execute in parallel. So I'm going to make it 1, 32, which means that I'm going to launch this kernel with 32 threads. What these numbers are currently, let's not worry about it, we'll come to that shortly. But does that mean that this is going to print hello world 32 times? Well, it actually does, right? So in this case, it's going to print hello world 32 times, and that is going to give you some sort of parallelism. Of course, the parallelism is not going to be useful for printf kind of processing. It should be used for more data parallel kind of processing, but this suffices for our purpose with respect to learning to print in parallel. Okay. So this seems to be okay, that we are going to launch this kernel with 32 threads, and that is going to allow us to run this 32 times. Will these threads, the 32 threads, execute in any order, or will it execute in a particular order? That needs to be checked, and that can be checked only when we know some sort of a thread ID with respect to each thread. So whether hello world 0 to 31, right? The thread ID is, if these are going to be from 0 to 31, then whether these thread IDs come to be 0 to 31 all the time, or these are mixed up, right? That will convey to us whether this is going to be parallel or not. Okay. We'll come to that in a minute. Sandeep says that this is going to be random. Okay. Any other suggestions? It turns out that yes, in general these are going to be random, but if you are restricting it to 32, it will not be random. It will always be from 0 to 31, and there is a reason behind it, which we are going to study. But yes, in general, if I launch it with more than 32 threads, it's going to come in some random order. Okay. So those of you who are probably aware of OpenMP programming on CPU, that is the multi-core programming, they might think about these threads as totally independent, which is the right thing to do as of now. But GPUs do not always have all the threads totally independent. There is a single instruction, multiple data format, SIMD style of processing, because of which 32 threads form a group, right? So that we call as a warp, and they are always going to execute in lockstep fashion, and therefore you will not always see these to be a random set of IDs, which we will come to as we move further. Yuvraj is asking, what is the maximum number I can try parallel threads? So in this case, you will be able to try up to 1024, right? So 1,1024 is the maximum that you will be able to try. Beyond that, we will have to change the first number, right? So this is like, yeah, I'll come to that part soon. Okay, so before that, since we have a diverse set of audience, I wanted to get going with some of the basic aspects related to the operating system and some of the terms that we'll be using repeatedly in all our 6 lectures. So what is meant by a process? So for example, a.out, notepad.exe, Chrome, all of these are, when they are running, these are called as processes. So processes are any program which is executing, we call it as a process. A thread is sometimes called as a lightweight process. Why it is called lightweight is because many threads might share some information, and they have some information which is specific to each thread. A process might have multiple threads. A process might have multiple threads. Very similar to what we saw just now. When we were running a.out, that hello world was printed by multiple threads. These threads might be executing on CPU or on GPU or on both. Okay. What is an operating system? Windows, Linux, Android, all of these are operating system examples, right? So OS is a software which manages the hardware, right? Because we cannot, as a user of the machine, we cannot directly deal with, okay, take these bytes, put it into the printer, take these bytes, put it into the, coming from the keyboard, etc. So we might have to deal with a large number of things, so that gets managed directly by the software, which we call as the operating system. So it's an interface between the user and the hardware. Okay. What is a hardware? Whatever you see and touch, all of that is hardware. For example, you can talk about a cache inside your machine. You can plug in different memories. You can increase the memory, reduce the memory of your machine, right? So that is your RAM. That is all your hardware. Right? Different cores which are present as part of your system on which threads are running, that is a hardware. Right? So whole dabba that you have, the whole machine, laptop, all the servers that you have, all of these are hardware. And the software component comes into picture, which tries to give life to it, right? So, I mean, in a more philosophical sense, as they say, hardware is the body and the software is the atma behind it, right? So the hardware remains fixed, whereas the atma might keep changing from one hardware component to another, right? So the software component takes charge of the hardware, it runs on the hardware, and also manages the hardware, which we call as the operating system. A core is a basic piece, basic unit, basic hardware on which a sequential programming will be run. So your parallel program might have some sequential component. In our case, we had the printf hello world that was being executed sequentially by each thread. So multiple threads were running in parallel, but one thread was running sequentially. So the core is essentially running your thread sequentially at any point in time. It's possible in some cases what we call as hyper-threading, etc., that the same core might run multiple threads, etc. But think about it from that perspective, that one core is associated with one thread at any point in time. It's possible that multiple threads at different times might be associated with the same core. Okay. And in general, a thread may jump from one core to another, especially on the CPU side. That means that one thread, if it is executing on one core at any point in time, doesn't mean that it will get restricted to that core. It's possible that the rest of the processing might be done on a different core by that particular thread. Right? So there is many-to-many mapping between the cores and the threads, especially on the CPU side. On the GPU side, also this is possible, but almost often it so happens that the same thread ends up running on the same core and maybe the same multiprocessor, and I'll come to that as we discuss more about the thread hierarchy. Right? Sandeep has a question that even the GPU threads run on the cores. Yes, the GPUs have their own cores. Just the number of cores might be different. For example, our CPUs typically have, let's say, a few tens of cores on the server end machines. Right? Your laptop might have 4 cores or 8 cores, quad-core machine or octa-core machine. GPU might have a few thousands of cores, and the threads are actually running on those. So you can launch a few thousands of threads on GPU at the same time. You can launch more, like on the CPU also we can launch, even if it has, let's say, 8 cores, you can launch it with 16 threads. That is all right. In a similar manner, on the GPU also, you can launch a kernel with more cores, more threads than the number of cores. Any questions on these basic aspects of these operating system concepts or parallel programming concepts? Okay. Even if you get these questions later, feel free to ask later, not an issue. Right? We all are learning. Okay, so let's do this small classwork. I am giving you a code, right? CPU sequential code, right? Our C code. And I want to convert it into the parallel code on the GPU side. Right? So please think about how you will do it with whatever we have learned so far, and if there is something additional that you require. I'll wait for a few seconds. Yeah, go ahead. Somebody was asking a question. Okay. Okay. So I didn't get any questions, but let's understand what needs to be done. Right? So what we want to do is to run a kernel in parallel, right? And how many threads with which we can launch it? Maybe we can launch it with n number of threads so that we can run this in parallel. Right? Okay, so Sandeep says that we can launch n threads synchronized. Right? So we'll understand what that synchronized is. But let's say that we launch it with this n number of threads, which is currently assumed to be 100. What is going to happen in that? So in that, I need to know what is I. Right? So in the sequential setting, it was okay. But so far we have not discussed how to find out how to give different eyes to different threads. One of the ways in which this can be done is that if I know as a thread my thread ID, which is going to be from 0 to n minus 1, that is 0 to 99, I'll be able to then print I into I, right? Thread ID into thread ID. That will be okay. So that is going to require me to use some sort of a thread ID concept, which we are going to define now. But there is something more which is being done in this if I parallelize it in this way. Right? That is what is implied with what Sandeep is calling as synchronized. So what happens when we are doing in parallel is that the output may not be 0, 1, 4, 9 like that, what we expect. But it might be a jumbling of these squares. Why? Because these different threads are running in parallel. On the sequential setting, exactly every time you run the code, you are going to get 0, 1, 4, 9, 16, 25, 36, exactly in that order, because they are running sequentially. Whereas, we are going to execute this kernel in parallel, where 99 threads are going to run in parallel, so they might print in arbitrary orders. There is no synchronization between them. So that is going to require us to change the program or understand that a parallel program might have some jumbling of the output where the instructions might execute it in arbitrary order, and I should be okay with it. If I am not okay with it, if I want exactly that sequential order, then maybe parallel processing is not the right thing for that kind of computation. Maybe you should actually execute it on the CPU. Does that mean that you cannot run sequential codes on the GPU? You can. Like we saw 1, 1 actually executes it with one thread. That might be a better processing to do if you at all you want to run some sequential code on the GPU. But by default, it is going to run in parallel. So let's understand that. But there is a question. Yuraj is saying, can we send parameters to the kernel? Yes, you will be able to pass parameters to the kernel, and we'll come back to this. But does that mean that can you pass I? Well, you can pass I. So let's say that I do a for loop on the CPU itself, but do a printf from the GPU. So I launch this D kernel and pass this I as a parameter, and then 100 invocations of this kernel prints all these values sequentially. Right? So this is also correct way of getting the same output, just that everything is sequentialized. In this case, we can take advantage of a little bit of parallelism on the GPU, right? And we can do this processing from the GPU. So let's understand how that can be done. So first things first, I am running this with a single thread, right? This is my kernel, which I am calling with triple left bracket and triple right bracket. I am not passing any parameter, and CPU is just waiting for that kernel to get over. What does this kernel do? By the way, these kernels must return void. You cannot return anything else. I mean, you cannot return anything from the GPU. If you want to modify something, you will have to pass some parameters to fun, which we'll study later. And this whole of this for loop can actually execute this printf %d I into I, which is completely sequential. And we would like to make this a little parallel. So that gets done by passing these as parameters to 1, n to the kernel launch configuration, right? So this we call as kernel launch configuration. So there are n threads that this kernel launches, and now I am defining a new variable called thread id x.x, which tells me what my ID is as a thread. Right? So if I print thread id x.x, I'm going to get the value 0, 1, 2, 3 all the way up to 99, and that I can print thread id x.x into itself, and that gives me the different squares, just that these are going to get jumbled up. Okay. Any questions on this parallel code? All right. So I'm going to go further, and now we are going to add another twist to this, right? So by the way, yeah, just remember that there is no loop here. So everything that is being done inside this kernel is being done by all the threads on the GPU, and therefore n threads are executing this in parallel. Okay, so just remember this. So therefore we don't need any for loop. Okay, there are a few questions. Why would the thread ID start from 0 and not another number? That is the default, Himanshu, that is decided that whenever we launch a kernel, all the threads are going to get unique ID starting from 0. Right? So that is the convention that we follow, that is given by the GPU hardware. Holmes says, please explain thread x.x once again. That is the thread ID which is being given to each thread. So you just put thread ID x.x and that is going to give you the number from 0 to 99 for this particular program. There is no date which we are going to count. Jagdish says, will fun 1, n that print the results sequentially? No. The result is going to get printed in parallel. So it's possible that 64 square might get printed first before 0 square is printed. That's possible. Away says, can we control thread IDs? Can assign custom IDs? No. These are fixed by the hardware. We cannot control those. Any other concerns? Alright. So we'll add more twist to it. Right? So what we are going to do now is that I am going to not print it, but I am going to store this in an array. Okay? All the squares I was computing before, which I was printing, I am going to store these in an array. Please spend a few seconds thinking about how you will implement this program, or whether you require something more to this. Meanwhile, I'll take up a question. Are both fun the same? No. The two funs are different. First fun was sequential on the GPU, which was running a for loop on the GPU. Okay? So it was a single thread which was running all the processing. So it was very similar to what happened on the CPU, just that CPU was printing it on the CPU and GPU was trying to print it from the CPU from the GPU, but the output actually gets buffered by the GPU driver back to the CPU screen, and therefore you will see the output on the GPU from GPU also on the CPU. The second fun that we did was 1, n instead of 1, 1. That is different. That is parallel. So this is similar to the difference between 1, 1 versus 1, 32. Right? So all the threads are running in parallel, and therefore they are printing this output or printing these squares in parallel to each other. So therefore these are different scenarios. Okay, so any suggestions on what we will require extra to parallelize this code? Yuvraj says, what is I loop through list of items in an array? I didn't understand that question properly. So
basically, I have an array of A of some 10 objects, and I want to loop those 10 objects parallelly.
So can we do that here? Yeah, exactly. So that is precisely what we require here, where I variable, if you want to parallelize this, the I variable is going to be mapped to the thread ID x.x, that is the individual thread's ID. So that is going to be required. And Sandeep says we need to share memory or transfer data, right? So that is the important part that we require here, extra part that we require here, that this array is going to be, needs to be accessible to the GPU, right? So is it not accessible? Can I not pass as a parameter? It turns out that we cannot pass it directly as a parameter, right? And there is a reason behind it, right? So I'll come to that. And then Koti has given a code which seems to be very correct with respect to what should be there inside the kernel. Away says get some return value from kernel function or pass array to kernel function. Yes, we should be able to do that. We cannot get the return value, but can we pass this array as a parameter? Unfortunately, that is going to cause some problem, and that's what we want to study via this. Govind says, what if we give the number of threads more than n? You can give number of threads more than n, that is not a problem, right? So just that when you are accessing this array, if the array size is n, then we'll have to worry about guarding that n with, if the thread ID is less than n, then we should go ahead, right? Otherwise there is no harm in launching the kernel. Just that in this case, since we had n items, we are launching it with n threads. But yes, soon we will have to modify this. Koti is asking how to handle race condition. We'll come to that when we worry about synchronization. Sandeep says going threads will be wasted. Yes, that is also correct. All right. So let me show you what we require, right? At least the part of the code. So what we want to do is essentially the same. We have this array, right? And in the end, I am printing it from the CPU, right? So that was not part of the original program, but this is for our understanding. And then I take Coty's suggestion of a of threadIDX.x equal to threadIDX.x into threadIDX.x. And I want to now pass a parameter, right? So that is what was suggestion given by Sandeep, I think, right? Yeah, that we need to possibly pass the parameter, but we cannot pass this a as a parameter, right? This a we cannot pass as a parameter. Why? Because CPU and GPU memories are separate. When we declare this a of n, int a of n, this array is allocated in the CPU memory. Even if you pass that as a parameter, that memory is going to be not accessible to the GPU. And therefore, it will try to access that address on the GPU, which will be probably a wrong address, a garbage address for the GPU, and therefore you are likely to get a seg fault when you try to run it on the GPU. Seg fault on the GPU, right? You might not even see it from the CPU. Right? So think about it this way, that if I say that go to, let's say, Rajaji Nagar, or let's say MG Road, right? If I don't tell you which city you should go to, there might be MG Road in almost every city. In a similar manner, the address is going to be the same across, I mean, let's say 0x1234, right? This hexadecimal value is a valid address. It will be the valid address on the CPU as well as on the GPU. So when you say that go to MG Road, you might go into your city, but I might have meant that go to Chennai's or IIT Madras's MG Road, right? So this is where you need to specify which device I am talking about, right? Unfortunately, by default, there is no common memory between CPU and GPU. There is a little bit of commonality, but for now, ignore that. So CPU and GPU memories are separate. So if I want to if I want to access something from the GPU, I need to transfer this memory to the GPU. And if I want to access something which was written onto the GPU, I need to get the data back to the CPU. In this case, the array I have allocated on the CPU, but I want to write it in the GPU, so I'll have to allocate the memory on the GPU. Okay. So this memory allocation on the GPU is done using a function similar to malloc. In this case, we'll call it as CUDA malloc. Right? So malloc allows us to allocate memory on the heap on the CPU. On the GPU side, we'll call it as CUDA malloc. The syntax of CUDA malloc is, and that is why I have this another pointer. Right? So DA is device specific array A. So ampersand of DA I pass as a parameter, and therefore DA is going to now start pointing to some memory which is allocated on the GPU. How much memory? That is defined by this n into size of int. That is the number of bytes that I allocate, similar to malloc. Just that in the case of malloc, I would have written DA equal to malloc n into size of int. Instead, I am doing CUDA malloc and pass ampersand of DA as the parameter. So DA changes after this, and it is pointing to a GPU memory, which is n into size of int bytes long. Okay. Now, using this memory, I can pass it as a parameter to the kernel. So every thread now has this A, which is pointing to a valid GPU memory. If I would have passed this A as a parameter, then it would have been an address on the CPU, and therefore this access would have resulted into a wrong access on the GPU because there is no memory allocated. But with CUDA malloc, we have memory allocated, which we are passing as a parameter. Okay. So once we have allocated this memory is written to by the GPU, and now I have the array on the GPU written to as 0, 1, 4, 9, 16. All the squares are ready on the GPU. Okay. But this memory is allocated on the GPU. Right? What we are printing is the array A, which is not populated at all. Can I directly write DA of I here? Unfortunately, no. The way I cannot access A on the GPU, I cannot access DA on the CPU. because DA is pointing to a memory on the GPU. So I cannot access it from the CPU memory. So what I have to do is to transfer that return square 014916 from GPU memory to CPU. How do I do that? That gets done using memcopy command. In CUDA's terms, it will be called as CUDA memcopy. The syntax is destination address, source address, how many bytes to transfer, and what is the direction of transfer. Since the direction of transfer could be from CPU to GPU as well as GPU to CPU. So therefore, in this case, I mentioned device to host. Device is GPU, host is CPU. And I am going to transfer n into size of int number of bytes from DA to A, from GPU to CPU, from device to host, and therefore now A contains all the squares. At this stage, I can now go and print it on the CPU. Okay. So this was our program which allows us to initialize an array on the GPU with squares and then copy it and print on the CPU. That requires us allocation using CUDA malloc on the GPU and transfer of data from GPU to CPU using CUDA memcopy. Any questions on this? Good observation, Yuraj. Is CUDA device synchronize required? In this case, it so happens that it is not required, but as a safety measure to remind yourself that you don't get into any issues, just add CDS there. But yes, in this case, CUDA device synchronize is not required, and the reason is that CUDA memcopy is a blocking call. So CUDA memcopy itself is going to not allow CPU to move ahead until CUDA memcopy is over, right? And CUDA memcopy deals with the GPU. Therefore, the fun is going to get over. CUDA memcopy is also going to get pushed into the same command queue, and therefore only when fun is over, CUDA memcopy is going to get executed. So CUDA memcopy is going to block with respect to fun as well as the CPU process, right? So that's a good observation. But yes, if you are concerned, just add CDS, CUDA device synchronize after every kernel call. That's okay. For now, it's not going to hurt us. Sandeep says, is there a way to avoid this transfer GPU to CPU? That is, you want to print directly from the GPU? Yes, you can do a printf directly from the GPU. But that is more like a syntactic sugar. When you do a printf, GPU does not have any associated screen with it, right? So it is anyway going to come back to the CPU. So there is a data transfer involved when you do a printf anyway, just that the programmer doesn't need to do it, it gets automatically handled. Oti says, what about deallocation of memory once operation is done? Very good point. I have not specified this, but similar to malloc and free, we have CUDA malloc and CUDA free. So CUDA free DA should be added before this. If you don't add it, then at the end of the program, all that is going to get deallocated automatically. But yes, as a good programming practice, we should have CUDA free at the end of the program whenever you don't need that memory. Good point. All right, so I'll move ahead from here. Sometimes you might require a global variable to be used, and you might think that, okay, I can have constant char star message, and I can use that as a parameter inside a kernel. Unfortunately, whatever you declare as globally, that is going to be allocated in CPU memory, and therefore you cannot use it inside the GPU code, right? So this is the GPU code. You can use it in the CPU code. That message you can use in the CPU code, right? That happens because the CPU GPU memories are different. However, if you are using a hash define, that might be okay. That you can use either CPU and GPU because there is no memory that is getting allocated. It's just a string replacement by the preprocessor. So that part is okay. All right. So just a recap of what we just quickly discussed, but don't think that this is the end of the lecture. We still have a lot to cover. So a CPU and a GPU, right, are two different pieces of hardware. They have their own memories, and therefore we need to transfer data back and forth, and the connection between them is via this PCI Express bus, and therefore the programmer needs to maintain these copies of variables, right? So at the very basic level, and this is changing in CUDA, but at the basic level, we need to maintain, the programmer needs to maintain these copies of variables, and it becomes programmer's responsibility to keep them in sync. Right? So there is a lot of programming burden onto the programmer, but that is required by default unless you use something better. Okay, let me tell you a little bit of about the overall program flow, but there is a question. Koti says, even in CPU, global variables not good as part of the thread safe. Yes, in this case I have written it as const, so that was probably okay, but if you have a read-write variables, then that is not a good idea to use global variables. In general also, if you have larger program, it's not a good idea to use global variables, even in sequential programs, but yes, more so in the GPU set, parallel setting. Jagdish is saying, what is a CUDA kernel? CUDA kernel is a function which needs to be run on the GPU, which you can call from the CPU, like our B kernel and fun in this case. A typical CUDA program flow starts with these two devices. You might have your data residing in the file system, inside, let's say, file or a database. So the first step is to load this data into CPU memory. That is what we typically have as part of our codes, typical simulation codes, etc., where you might read or generate some random data for processing, or read some, let's say, grid or a mesh or some geometry to process. The second one is that once you have data in CPU memory, you might want to transfer it to the GPU memory, whatever is the required part for parallel processing. We process it as the third step on the GPU in parallel. We get the results and then get those results back from GPU to CPU as the fourth step, and then make use of that on the CPU, typically sequentially, but you can also do parallel CPU execution also. For example, you can combine OpenMP and CUDA. This making use of the CPU might involve further calling GPU another kernel to process further data and so on. Okay. This processing can be done, for example, the loading data we typically use fread, or you can do a random number generation. We do CUDA memcopy from host to device, that is CPU to GPU, to transfer data from CPU to GPU. Then we call the kernel using some kernel call. Then getting the results back requires device to host, that is the opposite transfer, and then making use of results can be done in arbitrary ways. Okay. Typically, because of this CUDA memcopy, you will see that your codes might have two copies of the same variable. For example, we had A and DA. Similarly, you can have CPU array and GPU array, CPU matrix and GPU matrix, CPU graph and GPU graph, and so on. This is what you will typically see in several CUDA programs. Right? That happens because of this separate CPU and GPU memories. Okay, can somebody look at this code and tell me quickly what will be the output of this program? That will show whether you have understood whatever we have studied so far. Meanwhile, I'll take up Avesh's question. How data is copied? Is there any parallelism in it? Typically, so the copying happens via this PCI Express bus, which does have some amount of parallelism that depends upon the width of this PCI Express bus. So if it has a certain number of bits, those many bits you can transfer in parallel. Typically, we don't measure, we do measure it in terms of bits also, but typically it gets measured in terms of the throughput. How many gigabytes per second you are able to transfer, right? So it might have a few gigabytes of maybe a few hundreds of Mbps of transfer possible. In some of the latest, it may not always be PCI Express bus also. It can be a different technology. For example, you can have an NVLink technology, which is proprietary to NVIDIA, which might have a little bit of larger amount of throughput supported in this connection between CPU and GPU. Okay, so anybody has figured out what the output of this code is? Okay, let's understand what this code is doing. So it creates an array on the CPU, right? It also allocates a pointer which needs to be done CUDA malloc with. So that CUDA malloc happens with the GPU memory, and which has enough data to accommodate this string, right? Then I do a CUDA memcopy from CPU to GPU, and then launch a kernel with 32 threads. 32 is sufficient to process this. Each thread is going to increment this character, and therefore if you look at it, G is going to become H, B is going to become E, and KK are going to become LL, and therefore is going to print hello world. That /x is the hexadecimal value. 1F must be 31 because 32 is the ASCII value of space. So anyway, ignore that, but essentially it is going to print hello world, right? Which I copy from GPU to CPU and then print it on the CPU. Okay. All right, so we'll go ahead with this. I'll leave this as a homework exercise for you, where you can write a CUDA program to initialize an array of size 32, all zeros in parallel. You will have to make use of CUDA malloc as well as thread idx.x in this case. Okay. Now let's change this. Suppose I call it with 1,32. If I call it with 1,1024, will the code work? It turns out, as you will see, that the code still works. Right? Now change this array size to 8,000. Anything above 1024, and let's call the kernel with 1 comma those many number of threads. It is not going to work. Not going to work meaning you are not going to get those many threads because there is a limit on the second parameter that we pass to the kernel call. Right? So let's understand that. Right? So this also I leave as a homework exercise. So let's understand that from the perspective of a particular example. So what we are going to do in this case is that I have some amount of data, right? So 5 cross 6 matrix. So in this case, I am creating a matrix because matrix gets used in many of your applications or simulation-based systems. So I am taking that as an example. I allocate that matrix on GPU as well as on CPU. Okay. I call this kernel with n comma m as a 2 parameters. And I have said that a multiplication of these two is going to give me the number of threads. So I am launching it with n comma m number of threads. M is okay, but let's finish this part. I'll come back to this. What does that code do? It assigns different IDs to different elements of this matrix, which I have not shown yet here. I will ask you to probably think about it. And then once I have populated this matrix on the GPU, I am going to call this, copy this matrix from GPU to CPU, from device to host, and then print it as a 2D matrix in nice tabular fashion, as H matrix of II into number of columns plus J. So this is just printing of any 2D matrix. Based on n rows and n columns. So I'm now calling this kernel from n comma m. Now you have to think about, can you write a code corresponding to initialization of this matrix to unique ID. So essentially you have to initialize these entries from 0 to 29. Right? There are 30 threads, 30 fields, 30 array elements, and I would like to initialize those from 0 to 29. Please think about what extra you will require and whether you are able to write code corresponding to this. Meanwhile, I will take up a question. Sandeep says, how slash is incremented? Yeah, so it's not slash, it's a escape sequence. So it is /x followed by 2 hexadecimal digits. So /x defines a hexadecimal value, and that is going to be 2f. Not 2f, I think 1f. So that is going to be 16 plus f is 15. That is 31. That is the ASCII value 31, whichever character it is. So that 31 gets incremented to 32. Like /n is not 2 characters, it's a single character. So it's an escape sequence. Like that, you can specify any hexadecimal. Okay. So okay, so let me show you the code which requires us to use not only the thread ID, but now we are going to use a second parameter that we call as a block ID and block dimension. Okay, so what is a block and what is a thread? Let's understand this with an example. Let's say that all of you are inside your college and all of you are going for some picnic, let's say to Manali or something. All of you start from your hostel in different buses. A bus can accommodate, let's say, 40 students at a time. So the number of students who are going is going to be number of buses into 40, assuming that all of the buses are full. If I have to pinpoint the seat number of a student, I need to know the bus number and the individual. So if I know the seat number of a student and the bus number that the student is in, I can assign a unique ID to that student. Right? The bus number multiplied by 40 plus the seat number of that student, which is going to go from either 1 to 40 or 0 to 39. So any student in this whole carva of buses can be identified by a unique ID. Okay? That is precisely what we are doing, because we don't have luxury of a large bus which can accommodate all our threads. Right? So in this case, 30 threads can be accommodated into this, but this is just a small example. Beyond 1024, you cannot accommodate in one block of threads. That block of threads we are calling as our bus, which is going to Manali. So you require multiple buses. Those multiple buses, how many you require, is defined by this first parameter. And the number of students inside the bus is decided by the second parameter. And therefore, a multiplication of these two gives you the number of students who are going to Manali, or the number of threads which are running this GPU kernel in parallel. Okay. Inside if there is a single bus going, then you will be able to launch this as 1, n, and therefore the bus 0 itself. I mean, we don't need to worry about bus 0. That your seat number itself is going to be unique ID. That is what we were using so far. That was our thread ID x.x. That is the seat number inside a bus. But now I need to know the bus number as well as how many students are possibly seated, maximally seated inside bus. That is, in our example was 40. In this case, it is going to be this parameter m. M threads per thread block. This we will call as a thread block or a block of threads. So m threads per thread block are allowed. Therefore, this blockdim.x is going to be m, and therefore, essentially, this is going to be ii or block ID, and this is going to be jj or the thread ID, right? In our CPU versus GPU mapping. So block ID gives you the bus number that you are in. Thread ID gives you the seat number you are in. And together you can get a unique ID which is going to run from 0 to 29 in this case. Okay? And therefore, once you have this unique ID, you will be able to initialize this matrix with a unique identifier, in this case, this blockdim.x into block ID.x plus thread ID.x. Okay? I'll take up this question. How do we check whether memory is available in GPU RAM before allocating memory using CUDA malloc? We may not be able to check that, although there is a way you can get the remaining memory. But similar to malloc, like malloc returns null if there is not enough memory available. If CUDA malloc fails, the pointer that you pass as a parameter will turn out to have null value. Using that, we can check. We can ask, if multiple threads are being executed, then how do we ensure that there won't be any starvation or deadlocks? Do we require to have a resource lock on our threads? We'll worry about this in the synchronization part. But yes, in general, you might have to worry about it if there is a situation like this. Okay, if I want to launch this as 2, x, what should the x be? There is a question, how the n, m will be mapped between block ID and block D. So if you are launching this kernel with n, m, n is going to be going from 0 to, the block ID is going to go from 0 to n minus 1, and the thread ID is going to go from 0 to m minus 1. Right? So if I have to launch it with 2, m, 2, x, the x needs to be m into n by 2. Therefore, the total number of threads is going to become m into n. Right? In general, when you have a large amount of data, right? So in general, you are not going to deal with 30 threads, 30 data items. In general, you are going to require block size as large as 1024 or 512 or any multiple of 32. And in such cases, so in this case, I'm going to take some command line parameter, which might be some number which I'm taking as an input. I'm allocating an array of that much size, which I'm calling as vector on the GPU and H vector on the CPU. The number of blocks that I require, the number of buses that I require is going to be C log n divided by individual block size, because the bus size is fixed as 1024. It's just the number of blocks that I can launch with a very large value. And therefore, if my problem size is n, I require n divided by 1024 number of buses or blocks. And I can launch the kernel like this, right? So this is going to be your usual way in which you are going to launch a kernel. Number of blocks, comma, block size, which is going to be 1024. And then I'm going to copy the elements from vector to H vector, that is from device to host, that is from GPU to CPU, and print it on the device, print it on the host, or use it. Inside the kernel, I'm going to have this formula, which is going to give me a unique ID per thread. This is going to give me a unique ID per thread from 0 to n minus 1. Whatever be the value of n, 0 to n minus 1 is what I'll get. And vector of that I am going to give you, and I can do this parallel processing, data parallel processing using this. Okay. There are two issues with this code. Can somebody point out what are the two issues with this code? So remember this slide. This is how you are going to allocate memory and allocate the threads corresponding to arbitrarily sized problem size. Okay, so I can point you to where problems are, right? So one problem is here, another problem is here. So the first problem is that you are possibly going to have more threads than n. Imagine n is 1025. How many blocks will you launch it with? You will launch it with 2 blocks. If you launch it with 2 blocks or 2 buses, there are going to be 1024 into 2, 2048. But your array size is going to be n. That means that vector of anything beyond 1024 is going to be out of array bounds. That is one problem. The second problem is this is integer division. This is not floating point. So you will have to convert it into a floating point division, and then you will get the value 2. Otherwise, you will get value 1 and you might not write to all the threads, right? So, Eclair says n divided by block size unnecessary waste of blocks is there. Not blocks, but there will be some threads within the block which might have an unnecessary wastage. So some threads might get wasted, but in the larger scheme of things, it might be okay to waste one block as such. Alternatively, you can reduce the number of threads per block, and that might still be alright. Okay. So that is the change that we will require in this case. I'll leave this as a homework exercise. I'll leave this part. Also, this is also a little interesting from top500.org, which is the listing every 6 months. We keep track of what are the most powerful machines in the world, and currently, just as of June 2022, US has become the top one in this case, and you can check what is India's rank in this. Let me come quickly to matrix squaring in the last 5 minutes. Yeah, I'll go back to that last slide. So we require changes at these 2 locations. Right? And anyway, these slides are going to be visible to you, including the recording, so you should be able to go through it later. Okay, let me just go to matrix squaring. So matrix squaring is also another operation that we require often, sometimes in a more general setting, matrix multiplication. So a typical matrix squaring code on the CPU looks like this. I have a matrix. That square of that I want to store inside result, and let's say there is some matrix size, which in my case is going to be 64. So there are 3 loops involved, and result of II into matrix size plus JJ is equal to matrix this into matrix of this. plus equal to, and I assume that the matrix is result is initialized with 0 somewhere earlier. Right? When I run this on the CPU, on my CPU it takes 1.5 milliseconds. Okay. Let's try to parallelize this on the GPU. Right? So one of the ways in which I can parallelize is I can call this with 1 comma n and parallelize this outer ID. So how does the code look like in this case? The code looks like this, where that I that I was talking about, so the J and K loops remain the same. The I loop is run in parallel and therefore different threads take this value of I. That I is essentially the ID. So different threads are taking different iterations of I. So wherever I was using I earlier, I am going to use ID now. So different threads are now making things in parallel, and therefore I expect that this is going to have better parallelism. It turns out that when I run it on the GPU, after this parallelization, I get 6.391 seconds on milliseconds on my machine. This is slower, right? So that is not going to be very useful to me, although this is parallel, and this happens because the GPU clock is much slower compared to the CPU clock. Right? So it's not always the case that you just take any code, put it onto GPU, and it will start running nicely and give you speed up. That doesn't happen. We'll have to parallelize it properly. So one of the other ways in which we can parallelize is that can we parallelize it across 2 dimensions instead of 1. So instead of only I dimension, can I parallelize both I and J loops? Right? So that is going to be my second version. So I'm going to parallelize across both the block ID as well as the thread ID I can use in this case. So I have done some computation, but I could have directly used block ID x.x as well as thread ID x.x as I and J. Note that there are n square threads now instead of n threads in version 1. And now only K loop is present inside the kernel. And now if I try to check the parallel performance, that turns out to be better than even the CPU time. And you might be able to make further modifications to this, and you can check if this gives you any further benefits. But just to convey that, we have to parallelize properly. And GPUs are very useful when there is large amount of data parallel computation possible. Not always it is going to give you the performance benefit. Right? So that completes kind of our time. So I'm going to stop here. There is a little bit of last part, which is something which I have not been able to cover in this 1.5 hours. But I'm sure you will be able to figure this out, or if required, I can take up that in our next class if required. Right? So please go through this, and if there are any questions, I can take those up now. Okay, your assignment is primarily based on whatever we have covered with respect to different launch configurations. So you should be able to do this with whatever we have covered. Of course, I went very fast, but you will have to spend time thinking about it. You will get into code issues and falter and learn out of it and then succeed. Okay, Sandeep is saying your voice is breaking. Is it only for me or for everyone? Yeah, please let me know if that is breaking. For others, Yuvraj is saying, do we get the recordings? Yes, you will get the recordings by the end of the day. Himanshu says, I couldn't access the slides on the course spreadsheet. Was it uploaded? Not yet. Only after the course, or only after the lecture, I will upload it, both the recording as well as the slides. Yeah, Pradeep says that it is clear to him. Siva says, why the threads are limited to 1024? That is the limit given by the hardware, that in a particular bus, in a particular thread block, you can have maximum 1024 threads. That is because the thread block gets run on something called as a multiprocessor, and that has certain limitations of the hardware with respect to the execution unit, cache, etc. And therefore, that limit comes into picture. But as far as number of blocks is concerned, that is going to be arbitrarily large, or rather very, very large, and therefore it's not going to pose any problems. There are also some facilities which are provided to all the threads within a thread block. Right? So all these 1024 threads. For example, there is a local cache available to all of these, which is called as crashpad memory, as well as fast synchronization is given as a facility, and therefore these restrictions do come into picture. Okay, thanks Tony for confirming. Jagdish says, where can we access the assignment? It's posted on the Google group. Siddhartha says, which software can we use to compile and run the programs? Install CUDA, NVIDIA CUDA from its website. It is free, so you can install it and run. Alternatively, you can run it on Google Colab. Look at the video, which is given, link to it is given in the Google Sheet. Thanks, Pranav, for confirming. Nitin says, please add me to the Google group. My link got expired. Please drop me an email. I'll be able to add all of you, whosoever has expired links, to the Google group. Koti says assignment is there in group of NSM GPU. Thanks for confirming. Pradeep has written, write an email. Yes, thanks, Pradeep. Away says all GPUs have 1024 thread limit. No, most of the server end GPUs has 1024 limit as of today. It might increase later, and it was earlier smaller. So current limit typically for server end is larger. For lower end GPU, it's possible that you might be allowed only 512 or 768 threads, but you can. One thing is you can query these parameters using device query. The second thing is you can just try it out. Right? So does it depend upon vendor? Oh, we are talking about only NVIDIA GPUs right now. But yes, it does depend across vendors. This limit could be very different across vendors actually. Right. Yura said anyone who can support us when we get stuck while programming practice. We all will be available, myself, Pradeep, and our TAs. You just post your query on the Google group and we'll be able to answer it. The advantage of pushing it to the Google group is that if some of your friends in this course are also facing similar issue and they have solved this, they'll be able to help you also. Right? So that will be a big advantage. Sandeep says, will it be possible for you to...
Just one comment there. Just one comment there. Please don't post answers to the question in the Google group directly, okay? And don't ask for the final solution, okay? Just be sensitive to that.
Sure. Yeah, Sandeep is saying, will it be possible for you to dedicate 10 minutes for each class for question regarding the previous lesson? Sure, I'll do that. So what we'll do is, I'll join maybe 10 minutes, or we will join 10 minutes before, and we'll try to solve your problem. So feel free to join 10 minutes before or 5 minutes before, and we'll be able to take up questions in the earlier part. If required, we can take it from 5 to 5:10, but we'll try to join early, 10 minutes early, so that we will be able to answer your questions. Thanks, Sandeep, for that suggestion. Thank you. All right, so if there are no further questions, I am going to stop the recording here.